All right, so first thing, any questions from the homework that you'd like me to go over before we started class? All right, I will tell you that doing the homework and actually trying some of these problems is key to being able to pass the tests. All right, so if you haven't actually started working on some of the stuff in the chapters, I would highly suggest doing that before the test comes up in a couple weeks, especially the stuff we're going to be doing now, because chapter 6, a lot of that stuff, the integration stuff, you knew, so it's really just a couple of the formulas. This stuff is all new. This stuff was not covered in Calc 1 at all. So these are going to be, yes, new formulas, but also, yes, new processes and how we're doing integration. So it is definitely a benefit to you to be practicing these.
So, Professor, I know that you said that you wouldn't recommend we do all of the problems that follow in each of the sections. What would you say the cutoff is around, if you had to guess? Because you said don't go as far as like problems 80.
Yeah, so let's see, like, just because I have this chapter up. I would like for this section, the one we're going to do 7-1, I'd probably say up to like 36 or so, like those type of problems there. And that would give you a good understanding of what it is. So they do have a tendency to be like in order of complexity. So like up to 36, I think there's like 70 something problems in this section. So, and if you want to try a couple of the word problems, the application type problems, you can. So, but yeah, up to 36 for this section would probably be a good general cutoff point.
Okay, thank you.
No problem.
Professor, I just had like a question.
Yep.
Could I go to like the office hours this Thursday to get help on like the homework? It's just like you said, the algebra part is kind of confusing me.
Yeah, just send me a quick email just to remind me. So I'll stick around after class.
All right.
So, but yeah, that's not a problem at all. All right, integration by parts. So when we're doing differentiation, differentiation allows us to come up with what our derivative is. However, so integration is the opposite of that. So we're going backwards. So for every rule in differentiation, we have to have a corresponding integration rule. So one of the rules that you guys have learned already was the substitution rule. That's where you did the U substitution. And that really is the corresponding rule for the chain rule. So then that's one you guys covered, like it was like in section 4, chapter 4, something right at the beginning of integration. You do how to use substitution, and we're going to do more of that going forward. So this rule that we're going to look at, what's called integration by parts, is the rule that corresponds to the product rule. So the first thing let's look at is what actually the product rule is, just to give a little bit of a reminder of what the product rule was. So when we're taking the product or derivative of our product, you take the first times the derivative of the second, and then you add the second times the derivative of the first. So that is the product rule for derivatives. Now that we've got that rule, we're going to manipulate it a little bit to figure out what my rule is going to be when we're doing integration. So if we take the integral of both sides of this equation, so actually I'm going to go back here, I'm going to actually write it here. So if we take the integral of both sides of this, the integral and derivative cancel out, so you have f of x and g of x equals the integral of f of x, g prime of x, plus g of x, plus the integral of g of x, f prime of x. So we do the integral both sides. So now we can actually take this and we'll move a few things around to actually find my the way that I actually want to work this. So we look at this, we've got our integral right there. That's what I just did. And we rearrange it so that I'm taking the f or the g of f prime of x, and I'm moving it over to the other side. So I have the integral of f of x g prime of x dx equals f of x g of x minus the integral of g of x times f prime of x. So in essence, when we're looking at the integral,
Hey, Professor, could you slow down on that?
Oh, sure.
Repeat that, so.
I'm not going to move on. I'm not going to move past this point yet. So
So,
when we're
yeah,
look-
second step.
yeah, so basically this was my equation when I solved it when I integrated it. So all they're doing is they're taking this part here and moving it over to the other side. So I end up getting the integral of f of x g prime of x dx equals f of x g of x minus the integral of g of x f prime of x dx. So when we're taking the integral of a product, we're going to make one of them f of x and one of them the derivative of g of x. Okay. So because we can make it whatever we want in that respect, and that's going to help us find the actual function back at the beginning. So
Why do we want to take that part and subtract it out instead of taking the first part, the integral of f of x g prime of x?
it wouldn't have mattered.
Okay,
Because in the end, when we're doing it, the f of x and g of x are arbitrary. It doesn't make a difference which one you pick for each one. So it really doesn't matter. And actually, the way we're going to look at it, we're actually going to eliminate f of x's and g of x's, and we're going to use u's and v's and things instead. So it's a lot easier to look at,
okay.
which is what we're going to look at in the next slide. So this is a much easier way to look at it. Actually, I'm going to make it a little bit bigger. The integral of u dv equals uv minus the integral of v du. So same thing. That was my f of x. And that right there is the derivative of g of x. So all we're doing is we're substituting and we're making, so in essence, u is my f of x and v is my g of x. Okay. And then on the same concept of that, the du is the f prime of x dx, and the dv is the g prime of x dx. So this is what I'm going to use pretty much all the time. I just think it's simpler and more compact to write it. And it's going to be easy. And when we actually start doing the problems in a minute, I'm going to show you how we're going to pick things for each part. And the process actually works a lot easier than it sounds right now. All right, so everybody's got the equation down?
Yeah.
So what happened to the original side? For example, on the left side, it was the integral of f of x g prime x dx, right?
Yeah,
so
so that dv is g prime of x, or g prime of x and dx. That's what the dv represents.
Oh, Professor, could you go to that last slide real quick?
This one? Oh, no, wrong computer. This one.
Yeah, thank you.
No problem. So yeah, so basically all we're doing on this is, I'll do this one too. That's u, and this whole thing there is dv. That's u, that's v. Minus the integral of, that's v, and that whole thing right there is du.
All right, I got it. Thank you.
No problem. All right, let's actually look at one. All right, so I've got UdV equals UV. Yeah, I gotta make my V's a little sharper. V minus the integral of V du. So when we're setting this up, the first thing we have to do is I do V or U du and V dV. So I set those four things up. And now we're going to pick where they go in the two things. The two things I'm going to fill in are the U and the dV. Those are the two things I'm going to be able to get from my original problem. Okay. So for this one, I'm going to make my U X and my dV sine X. Okay. Are we good at that point? So right now, I just arbitrarily picked U to be X and dV to be sine X.
Normally, you wouldn't do that arbitrarily, though, right, Professor? So is there?
There is a rule, yes, and I will show you the rule in a few minutes. So yes, for this point right here, I just arbitrarily assigned one to each one. But those are the two you're always going to pull from the problem, is U and dV. Okay. I will show you why the rule and everything else in a minute. So, all right. So to get to du from U, I'm taking the derivative. So what is the derivative of X? So the derivative of X is what?
1.
1. So that's basically just dx. It's 1 dx. You can put the 1 or you don't have to put the 1. If you want to put it, you can. And now for the dv, to get back to v, I have to do the integral of it. Oh, I did forget to put the dx here. So what is the integral of sine of x?
Isn't it like negative cosine?
Yep. So that's negative cosine of x. All right. So now that we've got our four pieces, we can plug into my formula. So I'm just going to worry about after the integral of x sine x dx equals u, which is x, v, which is negative cosine of x, minus the integral of v, negative cosine of x. Du is just dx in this case. So once we've got the four pieces, we plug them back into the problem. So now this side is negative x cosine x. We can pull out the negative sign here, or you can leave it there. It doesn't make much of a difference. So that's the integral of cosine x dx. And the integral of cosine of x is sine of x. So it's sine of x plus. And that would be the answer. So this process is completely about this setup here. Horrible circle. That setup there is what makes the whole problem.
Was that your dx became a constant?
No,
Or
whenever
is
you
that-
take the integral of a function, remember when you do the derivative, your constants disappear. So when you do the integral, you actually have to add back in the constant, but the problem is we don't know what the constant is, so you put plus c.
Because the integral is not defined.
Correct. Right. It's not a definite integral. We don't have, if we have variable or numbers there, like an actual beginning and an end, you don't need to worry about the c because you're finding an exact point.
Okay.
All right. Now, in this problem, I said I arbitrarily picked the x and the sine x. I assigned them to those. So I'm going to switch it around. Because since I said I arbitrarily did it, we could have arbitrarily did it a different way. So I'm going to put the sine x at u, and the dx, the dv, I'm going to make that x. So what's the derivative of sine of x?
Cosine of x.
Cosine of x. Dx. What's the integral of dv or of x?
One half x squared.
Yeah, so x squared over 2. All right, so let's plug them into my problem. So I have sine of x squared over 2, minus the integral of x squared over 2 times cosine x dx. So if we simplify this down a little bit, I have x squared over 2 sine x minus 1/2 x squared cosine of x dx. Is that integral any easier to do than my original one? Because the entire reason of using this process is to make an integral that's easier to work with. This one got harder. Okay, so I said I arbitrarily picked where it was, but there's a reason on where you want to pick things because your goal is to make that integral easy to do. All right, so by putting the x as my u, like I did in the last problem here, it got rid of the x. So that was one less thing I had to worry about and one less thing I had to deal with. When I made the sine x here, it didn't get rid of anything. It made me a cosine x. And when I did the integral of x, it actually made the x more complicated. So by doing it this way, I actually didn't help myself. I made it a lot more work for me.
Because we would have to use another product rule to get that x squared cosine x.
Correct.
Right?
Yeah, you're going to end up basically doing another product rule and getting right back to your original problem, which isn't very helpful.
So just for reference, in this case, let's say neither method gave us the simple approach. I know this might be going ahead. What would our next tool be?
I'm going to show you that.
Oh,
We're going to do that. All right, so here is what they call the late principle. So basically, this is the order you want to pick your u for. If you have a logarithmic problem, you want to make that u. So that's the first thing. Any of your inverse trigonometric functions like tangent -1, sine -1, or sine -1, those things, that's second. Your algebraic problems is third. Then trigonometric problems, just your sine, cosine, tangents. And exponential is the very last thing you want to do.
what's
Sometimes,
inverse trigonometric?
so inverse trigonometric is your arc sines and stuff. So arc, sine, or the other way that they write it is sine -1. Those are inverse trigonometric functions.
What is meant by algebraic?
Anything like the x squared, those type of things.
All right.
So just simple, basically x terms.
So why is logarithmic at the top of the list? Is it because it's an easy?
Yeah, it's an easy,
Derivative?
it's an easy derivative and it works out normally. So that's why that one's first.
Could you give us an example of that, please?
Yeah, actually my next problem is going to be a logarithmic.
So if x and x squared are examples of algebraic, what's an example of an exponential? Wouldn't x
That's-
squared be exponent?
No, exponential is like e to the x or 2 to the x. Exponent is the x term.
I see.
So yeah, my next problem is actually a logarithmic problem. So
So logarithmic would be like log of x, right?
yep, or the one I'm going to do in a minute, it's ln of x, but yeah. So this is just a guide. It's not all encompassing. There is going to be certain situations where this is not necessarily the easiest way to do it, but it's a good starting point to try to do this first and then figure out, go from there. And we're going to do a couple of problems today that it gets a little bit confusing, but that's why I specifically chose them. Well, so you can start seeing other ways that the problems come out. So I figured I'd do all the problems, and then I'll let you guys do some of the other easier problems. This book actually does a pretty good job of picking its examples for that reason. So. All right, we got this down?
I got it now.
All right. Let's look at the next one. I should word it up higher. All right, so we're going to do ln of x dx. So this one looks really simple, right? Because it's just ln of x. The problem is we don't have an integral for ln of x. So it's like if you look at like the rules, you have integrals for all your algebra problems. We have some rules for a lot of the basic trig problems. But then there's other problems like this that looks really simple, but we don't really have a rule for it. So we're actually going to split this one up as the ln of x, and then we're going to actually use, so we're going to look at it this way, ln of x, and then we're going to do 1 dx. So we're going to use those two terms as my f of x and my g prime of x. So I've got my u du and my v dv. So I'm going to set my u, because going based on the rule we just looked at, I'm going to make my logarithm du, and then my du is 1 dx. Because if I made my dv ln of x, I'd be right where I am now. Wouldn't help me at all. So what's the derivative of ln of x?
One over x?
Yep. So that's 1 over x. And what's the integral of 1?
X.
So that's just x.
Would we add a constant too? Would it be x plus
Nope.
c?
Nope, you're going to do the c at the end.
Okay,
You don't have to do the c while you're doing the problem. We add it at the end, at the very end.
okay.
All right, so remember it's, my original function was, or uv minus the integral of v du. So I got the integral of ln of x equals ln of x. Actually, I'm going to put the x first in this case. Minus. Then we have x times 1 over x dx. So remember, the goal really, a lot of the times when you're looking at it, this right here, that right there is the key piece of how to make, what's going to make or break your problem is that du. So the reason why we want to do logarithms first is that becomes a really simple du. Even simpler sometimes than the algebraic ones, because I have, that turns it into an algebraic problem basically. So even if I have an algebraic problem for my dv, so my v becomes a little bit bigger, they're going to cancel each other out and simplify each other down. So that's really why you want to do your logarithms first. So, all right. So we look here, that's ln of x. And this one works out really nice because that basically becomes the integral of 1 dx. So that's just minus x plus c. Does that help you understand a little bit why we do the logarithm first?
Yes.
Right, because we want that d and du to cancel out.
Yeah. In this case, that works out and cancels out perfectly. It's like, remember, the whole process behind this is we want to make this integral really easy to do, or as simple as I can, or at least simpler than the original problem to do, as we're going to see in the next problem I'm going to do.
Wait, sir, I'm kind of confused. Like on the right side, like the integral x times 1 over x, could you like explain that? Like, I mean, how
So-
did it end up being x? I mean,
Oh, because when you basically the x and the 1 over x cancels out, becomes 1.
all right.
So that basically became that. And that's the integral of 1 is just x. Let's look at another one. All right, the integral of e to the x, or x squared e to the x. So and if you look at the book, they actually write them a little in a different order, but it doesn't really matter. All right, so which one am I going to make my e to the u? I mean, which one am I going to make my u? Or x squared or e to the x?
E to the x.
So let's go back and look. So
X squared.
exponential is the last one. Exponential you always want to make as your last one because it stays the same, right? So if you put e to the x as u, du is e to the x. It's not going to make my problem any simpler because nothing's changing there. Or if I make it my e or dv, v is also e to the x. So again, it doesn't change. So you want the du to get simpler as we go, because that's the piece that I want to get rid of. So I'm going to make my u x squared and my dv e to the x. So my du will become 2x dx. And my dv will become, or my v, I mean, will become e to the x. So again, remember, you want your du to get simpler as you go. So we have uv minus the integral of v du. So I've got x squared times e to the x minus the integral of e to the x times 2x to the x.
And you take out that 2 in
Yep.
front of the 2.
Yep, we can take out the 2, so let's simplify this down a little bit. X squared e to the x minus 2 x e to the x dx. All right, so can I do this integral right out now? No, still can't just do it. However, is it simpler than my original inequality? And that's yes. Even though I'm gonna have to do integration by parts again for this one, because I still have a product there. But I changed my x squared to x. So it's one less, now I have one less exponent. So my next step, that x is basically gonna vanish. So if we just look at the integral part, the x e to the x dx, I'm going to make u x and my dv dx e to the x, which means my x is going to just become, excuse me, disappear. And my v will be just come e to the x. So sometimes when you're doing it, you're going to have to do your integration by parts twice. And that's okay. It's just a little extra work. So this one's going to become x e to the x minus the integral of e to the x dx. So now I have x e to the x minus e to the x plus b.
And now we have to plug that back in to the last
Very
step
good.
of the first problem.
Very good. Yes. Actually, what I was just going to say, that's not my answer. This part right here is this part right there. So I've got to plug that back in. So this part is going in this part. So my final equation is x squared e to the x minus 2 times x e to the x minus e to the x plus b. So we can simplify this or break this out a little bit. So it's x e to the x minus 2 x e to the x minus 2 e to the x plus b.
Wouldn't it be plus 2 e to the x, Professor?
Yeah. Oh, you're right. It is plus 2. Right. Sorry, 2 negatives. Good catch. Bad part about it is I think I actually said plus 2 e dx. I just didn't write it. hold on one second. I got something. All right, so that's also the reason why you want to make the V or the DV, the E, the X, because it just stays there. It doesn't make the problem easier or harder. It just stays.
Are you able to get a polynomial or factor x squared minus 2x plus 2 real quickly, just as a side gag?
Oh, but this one here?
Yeah, x squared minus 2x plus 2.
Yeah, I could. Yeah, you could take that out. So you could reduce it down so it's this x squared minus 2x plus 2. Yeah, you could do that. if you
Right, but
want.
what I'm saying is, what would the two factors be? Like, what's your approach to that? Just like as a quick.
Oh, honestly, I would just use the quadratic formula for this one because there isn't actually integral answers for that one. You can't come up with two numbers that multiply to 2 and add a -2. So it's not going to be an integral answer. So honestly, I just use the quadratic formula for it.
Oh, so the way you determine that is because, okay, I have to come up with two numbers that multiply to 2 that add to -2.
Correct. Yep.
Oh, I never thought about it.
Wait, you had to have forgotten because I guarantee your algebra 2 teacher in high school taught that exactly like that. You probably just totally forgot it.
For a question, I don't need to do the quadratic formula because what you just squared is the final answer. I don't have to do the quadratic formula, right?
No. No.
Oh,
What I
thank God.
boxed, that's as far as you have to go. You don't even have to factor out the E to the X.
All right, that makes life easier. Thank God.
Yeah, this boxed answer right here, that's the answer. That's as far as you have to go. You're good at that answer. So you can simplify it down if you wanted to. He was asking the algebra part, which is fine. Because, as horrible as this is going to sound, one of the sections that we're going to be doing, you're going to have to remember how to factor. So that is not a bad thing to get a question on right now. All right. Let's do another one.
So you said that we ended up using this method because we had to integrate by parts a second time because we still had a product.
Correct. Yep.
And in the first example, we had the integral of x over x times 1 over x dx. And that is a product, but technically it cancels out to just be x over x.
Right. So it's simplified down. So I no longer have the product.
So if we simplify as far as we can and we're still looking at a product, we have to integrate by parts a second time.
Yes, unless
At
so
least.
the only other option that you have is sometimes you can do U substitution, which might help you work it out. So like you could say, so let me find a U substitution problem real quick.
When you say substitution, do you mean like what we did for chain rule?
Yeah, basically. So here, let me do one real quick. So if we had a problem like this, the integral of, let's make sure this one actually works out right. Yeah. So technically this is a product, correct?
Yeah.
Okay, but if I set U to be 1 plus x squared, du is 2x dx. Correct?
Okay.
That is true, yes.
Okay. So what I can do is if I rearrange this problem, this right here, that becomes the square root of u. And this becomes du.
I thought wouldn't it be, oh yeah, the square root of u, sorry.
So now, see, so that was another way, that was a way we got rid of the product. The problem is this only works when you can make a substitution that gets rid of the other part. So there are situations where even though it's a product, you don't necessarily have to use integration by parts to solve it. And when we get through all the different methods, the first thing you always want to look for is, can I do substitution? Because this is a heck of a lot easier than doing integration by parts. Although you could technically do this by integration by parts, you do not want to.
For the sake of refreshing, could you finish that?
I'm going
problem?
to. Yeah, I'm gonna. So the integral of the square root of u is it 2/3? Yeah. So 2/3 u to the 3/2. Because in essence, you change the square root of u to the 1/2 plus c. And then then all we do is we take what u was and plug it back in. So the final answer is 2/3 1 plus x squared to the 3/2 plus c. So when you do u substitution, once you get your final answer, you have to replace the u back with what the original problem was.
And in
We
this
don't have to
case, we
worry about
didn't,
the du?
The du is gone by the integration.
Okay.
and in this case, we wouldn't have to designate a V or a DV.
Correct, because you're not doing integration by parts. You're doing u substitution.
Is this its own thing as
Parts is
integration
more
by
of an
sub?
advanced technique. Oh, then substitution. Sorry, cut you off.
So yeah, so this is actually the substitution rule. This is just a simple substitution rule problem. You're not doing integration by parts or anything else with this one. So this isn't a subset of the integration by parts. This is actually a different rule. This is the rule that goes along with the chain rule. So if you think about what the chain rule said, was when you're doing it, you're taking the integral, you take the 1 plus the x squared, you do the integral of that, or I mean, that's the integral, the derivative of that times the derivative of the whole thing if that didn't exist. Remember the chain rule?
Chain rule is confusing.
All right, so I'll do that one real quick and then we'll do the other one. So let's go back to my fix this problem. So the chain rule. So it was 1 plus x squared to the 3/2 plus c. So the chain rule says you take the derivative of this, which is 2x, and you multiply it by the derivative of the whole thing. So now we're basically going to do the derivative of u to the 3/2. So the derivative of that would be the square root of 1 plus x squared. Actually, so this derivative of that would be u to the 1/2. So it was the derivative of the inside piece times the derivative of the function if the inside piece was just a single letter, like x. So if that's f of x, that's f prime of x. So substitution rule is just a reversal of that. That's why we don't have v's and everything else in it, because we're only doing one substitution. But I wanted to give you an example of where it's a product, but you don't have to necessarily do integration by parts.
To make sure I'm good as well. you can do the substitution rule for the one up there with the last problem with the integration,
Yep,
because the integration automatically created du in the problem itself. So you didn't have to do the chain rule to create the du for you.
right. So the reason we were able to do substitution for this one is because this part right in here, the derivative of that gave me that.
Mm-hmm. And because you could do that, you didn't have to use the chain rule. You could just substitute directly and find
Correct.
your answer.
Yes.
Okay,
I can do the
I was just making
substitution.
sure because I was trying to figure out like how do you do this without doing some derivatives of other stuff? Throw another thing in there. No, it makes sense. Thank you.
Yep, no problem. Yeah, so it's just, that's the piece. Like if it works, use substitution all day. If that doesn't work, that's when we have to do the product rule. And one of the things that we're going to do once I get through all the rules, like section 7.5 actually goes through all the rules and how you want to decide when you're going to use them, which is going to be the most important part for the test, because that's what you're going to need to do for the test. You're going to have to look at the problem, and it's not going to say, use the product rule here, or use the integration by parts. It's just going to say, here's a problem, integrate it. And you have to figure out which rule you're going to use to do that integration. So, all right. Next screwy one. So the integral of e to the x sine x. So u du and v dv.
Oh, sorry, Professor. I was talking. I didn't realize I was muted the whole time.
Oh, no problem. What's up?
To finish back to the chain rule, does that mean that, just to make sure that I got it right, does that mean that the answer to that to the problem that you posed there would be 2x? So the derivative of what you posed there, 2/3 times 1 plus x squared times 3/2. The answer to that, the final answer would be that would be 2x times 1 plus x squared to the 1/2.
Yeah, or the square root of 1 plus x squared. Yeah.
So you just plug in the u back into the, after you take its derivative.
So you're basically, once you do the derivative of this part over here, which gives you the u to the 1/2, you're just replacing it back with that 1 plus x squared.
Oh, okay. And then multiplying it by the 2x.
By the derivative of that u. Yeah.
Cool.
All right. So if we go back to our wonderful, that rule that we looked at the beginning, the problem that I have right now has a trigonometric problem and an exponential problem. The two bottom of the barrel things. There's a reason why they're at the bottom of the barrel. So which one should I make u? E to the x or sine x?
Sine x.
Yep. So that's sine x. And that's e to the x. So v will be e to the x, and du will be cosine x dx. All right, so let's do our problem. So I've got, sorry. You'll notice there's a reason I always keep writing this, and it's not, it is for you, but it's also a great habit to get into, to have that above your problem. So this way you remember where you're plugging it in. It also tells you, oh, I'm doing integration by parts for this problem. So, and it also reminds me, because I have a tendency to get U's and V's mixed up sometimes. So, all right, so we've got integral of e to the x sine x dx is sine x times e to the x minus the integral of e to the x times cosine dx. All right, so simplify this a little bit. So I'll put the EX in the front. Minus integral of e to the x cosine x dx. So at this point, I'm kind of stuck again. I'm at the point where I'm going to have to do integration by parts again. So because I still have a cosine of x in there, and it's not really much different than my original problem, except it's a cosine of x. All right. So let's do it again. So same thing. I'm going to make my u cosine of x and my d at v e to the x. So that's still going to be e to the x. And the derivative of cosine of x is what?
Negative sine of x?
Yeah.
Dx?
Yep. It's the negative sine of x dx. So that was my original problem, and I was doing it there. All right, so we've got the integral of e to the x cosine x dx is e to the x cosine x minus the integral of e to the x negative sine x dx. So it simplifies, so e to the x cosine x plus the integral of e to the x sine x dx.
Wouldn't a problem like this just go on infinitely, or am I thinking about this wrong?
Very good. I'm glad somebody caught that. Yes, this would go on infinitely, which would suck. And you don't want to have to go on infinitely. We hate math that goes on infinitely. But there's a solution to this problem. So right now, this part right here is this part right here in my original problem. Okay. So now I'm going to put all this together so we can see something. I know I'm going to write and then I'll switch my screen because I want to have it all at the same time. So you guys can finish writing this down if you want. All right. So that's what I have. I have the integral of e to the x sine x dx equals e to the x sine x minus, in parentheses, e to the x cosine x plus e to the x sine x dx. So you said it goes on infinitely because what was the integral that I got in my second step?
Well, the sine and cosine are just going to keep alternating. The e is never going to go away. So that's what made me just think of that.
Right. Where else on the screen do I see that?
First part.
The original problem that I was originally trying to do. Okay. This is one of those ones that I don't think, unless you're really good at math, when you're typically trying to solve a problem, you only work on one side of the equation. You only work on one side. So in all the problems that we've done so far, the original problem never changed. I just kept looking at the equal sign and dealing with it. However, there is a reason you write the other side of the equation, because I can use the other side of the equation. So we're going to simplify this problem a little bit so we can see something. I'm going to get rid of the parentheses. If I was to add this, to this side. I would have two of them, right? So I would have two. Okay, that step. I'm not going to ask if the step makes sense, because for most of you, I don't think that would step make sense. It's like, why am I doing it this? Do you understand what I did? Is a better answer to that question.
Yes.
Okay. So the reason why we can do it is because they're on both sides of the equation. Sometimes, like this way, because it was negative, it actually moved over and it didn't cancel itself out, which you don't want to do. By bringing it over, though, I have two of them. Now I'm just going to divide both sides by 2.
Did you say we don't want to cancel it out?
Right. So what it is, so if this was a positive on the right side, I would have to subtract it from both sides and it would cancel each other out. That I don't want to do. I want to cancel it out from one side and have it left on the other side still. So I canceled it out on the right side, but I'd have 2 of them now on the left side.
I feel like canceling out on the other side would have made our lives easier.
Yeah, you wouldn't have your original problem anymore, though.
Oh,
So therefore, your answer would be no answer. So now we actually have an answer. Our answer is e to the x sine x minus e to the x cosine x divided by 2.
Isn't sine of x minus cosine of x some sort of identity?
It would be if it was squared. It's
Oh,
sine of
okay.
x, it's sine squared of x minus cosine squared of x. Or no, sine squared of x plus cosine squared of x equals 1. So yeah, even if you factored out the e to the x, sine of x minus cosine of x doesn't do anything.
So kind of to summarize this stuff, once we get an identity, or once we get the left side of the equation as a through the product rule or through the integration by parts, once we get the same value that's on the left side, on the right side, we just do opposite.
Yeah, so it's like basically it's one of those things that you just have to realize that when you start to loop, you need to get out of the loop somehow. So in one of like the problem that we did a little bit ago, the problem that we did, we had to do the integration by parts twice. And this one, it never actually looped. It was still getting smaller every time we were going. So even though we had an integration by parts, okay, we can do it again. And this one, what we started to notice would actually, I can't remember what one of you said, is that it seems to keep repeating itself. So it's going to keep going for infinity because sine is going to just keep switching back between sine and cosine. That's actually the reason why trig is so far down on that list, because it does do that. The reason the integrate or the exponential is even lower is because the exponential never changes. E to the x is never going to change. All right. So, and even if it was 2 to the x, it'd be over ln of squared. It'd be just over a constant, and you still would have 2 to the x. So that part never actually changes. So that's why that's on the very bottom of the list, because it's not going to simplify. Where your trig ones kind of keep repeating themselves, especially the sines and cosines. So, in this type of problem, when you start to see that loop, that's when you go, okay, I need to do something else. And that's where looking at the other side of the equation can help you with that. All right. One more problem I'm going to do. All right, let's do a definite integral. No, I did forget to put my plus C on this one. On the last one. But let's do a definite integral. All right, so I have one function in this one, right? I just have the arctangent of x. I don't have another term in this problem. So in the last problem, when I didn't have a second term, what did I use? So remember when I did the
One.
the ln of it, the ln, I just used one, right? For my other term. So the one, it was on this one, remember when I just had the ln of x, I just made my dv 1. And I'm going to do something similar in this problem. So in both of those situations, though, the piece that I'm doing is above the algebraic. Okay, so the logarithmic and the inverse trig are both above algebraic, because technically 1 is an algebraic problem. If I'm just plugging in a 1, that's algebraic. So if I do the derivative of 1, it comes out to be 0. So that's not going to really help me much. So this process normally only works when we're doing logarithmic and inverse trigonometric functions. When you only have that and you have to do a product, the integration by parts. So I'm going to make my u tangent negative 1 of x, in my dv 1 dx. So that means my v is x. And I will totally understand if you do not remember what the derivative of the arctangent of x is. The derivative of the arctangent of x is 1 over 1 plus x squared. And I totally agree if you don't remember it, because I don't remember it. I have to look it up. So those are just not ones we use every day.
Is that something we'll be able to look up on the test if we have a test with this on it?
One of the things I said, I would definitely have a cheat sheet. And those are things that I put down. So when you're doing the practice test, you're not going to see something crazy that on the test that wasn't on the practice test. So if the practice test has arctangents, stuff like that on it, you're probably going to see that in the actual test. So I put some of those things down in your that cheat sheet.
Okay, so like you were just saying, if I see arctan on
The
my practice test, write it down on my cheat sheet.
Yes, because you're probably going to need it for the actual test. So
Gotcha.
when you're doing the practice test, if it's something you have to go flip in the book to find, write it down in your cheat sheet.
Thank you.
No problem. All right. So now let's do my problem, because now we've got all the pieces. So we've got the integral of, and now this one's a definite integral, so we're going to have to do some calculations at the end. So equals x tangent 1 of x minus the integral of x over 1 plus x squared dx. So, and then, so this whole problem still has to be evaluated on 0 to 1. So we still have to plug in the 0 to 1 on the beginning part too.
Is product rule is integration by parts and kind of rephrasing 1 plus x squared as 1 plus x squared to the negative 1 the best approach to kind of solve this integration?
Yeah. However, good idea, but no, there actually is an easier way to do this one. But yeah, so sometimes we're going to actually do one a little bit later on that actually deals with division. But yeah, sometimes actually that's a really hard method to do it. So sometimes actually moving things up will make your life a little bit easier to do. In this situation, it actually does not. So in this situation, let's actually look at this in terms of a U substitution. So remember, you always want, if you have, like, sometimes when you're looking at the problems, U substitution makes your life a lot easier. And U substitution does not mean you have to use the letter U, because in this problem, not, because I've already used U. So I'm just going to look at this integral right here. So 0 to 1 of x over 1 plus x squared. All right. Oh, and one other thing, this does not equal this. Those two are not equal to each other. And I'm saying that because I've seen that happen. You can split the top addition, but you can't split the bottom addition. So if it was flipped, you could absolutely do that. So we're going to say m is 1 plus x squared. So what's dm? What's the derivative of 1 plus x squared?
2x.
2x. So I'm going to, this is also the 1/2 dm is just x dx. Okay, notice right here, I have x dx. So this problem is the integral from 0 to 1 of 1 over m dm, and I can bring the 1/2 out in front. Actually, let me write that a little bit better. I can pull the 1/2 out, and it's 1 over m ds.
Wait, could you slow down, Professor,
Yep.
a second on that? So yeah, so dm equals 2x, right?
Yep.
And then we put that. Well,
And since I don't have the 2 in the original problem, I only have an x. That's why I moved the 2 over to the other side to get the 1/2.
So the derivative of 1 plus x squared is 2x. That makes sense to me.
Yes.
Now, where did you go from 2x to 1/2 dm?
All right. Let me get another screen so I can actually do this. So you can see it a little bit. So I can write a little better. All right. So I have x over 1 plus x squared dx. So I'm going to say m is 1 plus x squared. So
Gotcha.
dx is 2x dx. Okay, we're good to there, right?
Yep.
All right. So I'm going to rearrange this problem a little bit. So right now I have this, but in my problem I have 2x dx, right? So I need to move this 2 over here. And I do that by dividing. So that's how I get 1/2 dm equals x dx.
Okay.
Okay? So now the integral becomes 1 over m, and then it's 1/2 dm. And I can pull the 1/2 out.
Oh, that's clever. So the step of simplifying so that we get the x dx on one side. This is just a matter of being clever, I guess, right? It's just really recognizing that dm has that extra 2 sticking around. So if you take it off to the other side, you get the x dx.
Correct. Yep.
Is that a rule or a specific something that, you know?
This right here is U substitution. This is the substitution rule. The nice thing that works out really well with this, so is whenever you have, it's a constant. And you're gonna see this right here, what I'm doing on this screen, a lot when you're doing U substitution. So it's one of those things that you should start to recognize because you're gonna do that movement right there in a ton of problems. So, because your goal is to basically get this piece at the end to be very simplified. And a lot of times, the first thing you do to constants is pull it out anyway. So even if there was a 2 up here, a lot of times you'd have brought it out in front of the square or the integral right off the start. So you wouldn't even have thought that 2 wouldn't have been part of the problem that you've been using. It would have just been the x.
Can we say that again?
You can take any constant that's inside of integral and pull it outside. So even if I had a 2 up there in the original problem, which I don't in this case, but even if I did, the first thing a lot of people would do is pull it out in front. Because you want the integral to be as simplified as possible, and constants have a tendency to make it a little more messy. So by taking the 2 out, you still would have only had x dx in the actual problem.
So now that you've got 1/2 the integral of 1 over m dm, you have to substitute back
Well,
in.
now we're
for
going to
m.
do that integration. Now we have to
Before
do the
you-
integral.
Before you substitute back in?
Yes, because if we substitute back in, we're back to where we started.
Gotcha.
So we have to do the integral and then substitute back in. So the integral of 1 over m is ln of x. So in this case, it's 1/2 ln of 1 plus x squared.
And the dm goes away because that's just telling us to take the
We're doing-
derivative in terms of m.
Correct. Yep.
So in this case, Professor, we obviously wouldn't have done -1, kind of thought of as 1 over the m as m to the -1, right? Because we had one, it would have just been m to the 0, which would have given us 1.
Right. So yeah,
And we
so
can
that's
divide by
why when you're doing the power rule, yeah, if you brought it up, you'd have m to the -1. So if you try to use that rule, you would get m to the 0, which is 1, which which doesn't work. So
You
because,
also can't divide by 0.
right, you have to divide by 0, right, which makes it not work. That's why 1 over m, the derivative or the integral of that is ln of m. That's where that piece comes into play. And there's actually a lot more reasons why, but that's why it works that way.
Is there like a metaphysical reason why the ln exists to, account for division by 0?
Well, no, because the ln actually exists to get rid of it's the natural log for e. So your logarithms everything has to have an inverse to it. So your exponential functions, the inverse to it is your logarithms. And the ln exists because of it's the natural log, which is the inverse to e. So it just happens to work in integration that the 1 over x ends up becoming the ln of x in your functions. I haven't dug into it deep enough to explain to you exactly why, but it just happens to work out that way. But that's not why ln of x existed. ln of x existed well before we actually did calculus and integration.
All right, and this was only one piece of our
Yeah, we're not done with this problem.
pie here. And we still have to evaluate at 0 to 1.
Yes, so yeah, actually, so my original problem, so we just did this part right here. So my actual answer right here is x tangent -1 of x minus, what was it, ln of 1 plus x squared. And we're evaluating this from 0 to 1.
Wasn't it 1/2 ln 1
Oh, you're
plus
right.
x squared?
Hold on. Yes, I did miss the 1/2. 1/2. What happens when I'm flipping between screens? All right. Let's evaluate. All right, so let's plug in 1. So x is 1. The arctangent of 1 so the question is, so which angle is going to give me tangent of 1? And that happens to be pi over 4. Is where tangent equals 1. Minus 1/2 ln 1. So that would be ln of 2. So minus 1/2 ln of 2. So that's that first part. And then it's minus the 0. So the nice thing is it's 0, tangent negative 1 of 0. So that's 0 right off the start there. And then minus 1/2 ln of 1.
Is pi over 4 45 degrees angles? Is that the idea?
Yeah,
So because the SOHCAHTOA opposite adjacent equals 1, right? So tan of x equals 1.
yes. So tangent of x equals 1. And the value of x is pi over 4 in that case. So I've got pi over 4 minus 1/2 ln of 2 plus 1/2 ln of 1. Now, ln of 1 is 0. So my final answer is pi over 4 minus ln of 2 over 2.
So would you want us to have evaluated that far if we had given you the answer pi over 4 minus 1/2 ln of 2 plus 1/2 ln of 1?
I look at that, I might have taken off a point because I don't, at that point, I probably would have realized we didn't realize that ln of 1 is 0.
Right.
But I wouldn't mark the whole problem wrong. It's like I'd probably just take off a point for it.
Okay.
So it'd be no different than saying your answer was 4/6 instead of reducing it to 2/3 type thing.
Gotcha.
So one thing, when you do your test on WebAssign, they're very particular in their answers. So make sure you do all your work out on paper. If you get a problem wrong on WebAssign, it's not going to tell you what your answer was. However, if you get a problem wrong and you think you did it correct, just take a picture of your work and send it to me, and I can give you points based on your work as well. All right. So if you got a problem wrong and I look at your work and you have it right, but you just didn't type the problem in the way they were looking for, I can go back and modify and give you the points for those questions. So. Right. Okay. And on that, we're done.